All right. Hi, everybody. Thank you for coming on this Tuesday that feels like a Monday. Um, a few announcements as we go. Um, the summer research program application is still open, I think. If you're interested in that, I recommend you Google St. Mary's Summer Research Program. That'll take you to their website and tell you all these nice things. Um, There's people you can email if you have questions about the program. I'm participating in the program, so if you want to do research with me, or there's a lot of other people that can sponsor projects. Um, so yeah, that's an option for you. Um, I'm looking forward to it. I haven't done this before, so I think it's going to be fun. I will also say that if you're interested in kind of learning what is research about, um, if you want to do some research with me, I have some projects that I would like students to work on. Um, and so research in this context generally means like I've got a problem, but I don't know the solution. So it's not quite like class problems where I give you something to do and then I know what the correct answer is. It's more of exploring where I kind of have an idea of what I think the answer is going to be, but I don't know for sure. And so the types of research I have off the top of my head, there's some like reading scientific papers to do. There may be like some small coding projects that I can put you on. So if you're interested in that, come talk with me. Not required at all, but I just figured I would put that out there. Um, there's also a tech club, also not required. Just want to make sure that it's on your radar. We're planning to meet maybe every other week or maybe once a month. We're still trying to figure that out. And that's a space for people interested in coding or computers to just come together and talk about things. Um, there's going to be a table at the club fair on Friday, I believe. Thanks for everyone who submitted the first week feedback. I really appreciate that. Just trying to see how things are going in general the first week. And then have something for you. I'll give you the whole deck. Pass around. Okay, so I'm passing around homework one, which is also on Canvas. You don't have to complete it on this page, but just so that you have a hard copy. Um, yeah, so you can do it on a separate sheet of paper. You can do it digitally if you want. The idea is I would like you to draw pictures. Let me pull it up. 485. Yeah, so the point of chapter one is to kind of go over graphs in general. And so I would like you to start brainstorming of just what are different kinds of graphs that you could see out in the wild. They could be like paths on campus or something completely different that I can't think of. So the idea is just for you to practice and kind of ask, what could be a graph? And then you write that down. So yeah, so they don't have to be super complicated. They don't have to be super intricate. Just get the ideas out there and we'll get rolling. If you've got questions, if you have an idea and you want to talk it through, come talk with me. This is going to be due next Thursday. So that's the timeline that you have for that. And I've updated that on Canvas. All right, any questions before we get going? All right. Let me figure out screen sharing. That's over there. And I will share on Zoom PowerPoint. All right. So just to remind you where we kind of left off, we've been looking at different types of graphs, kind of just to get us started of what sort of graphs will we be talking about this semester to give you an overview of where we're going. So we started we've talked about weighted graphs a little bit, where that's one of the first things that you see on the packet. And weighted graphs are just graphs with numbers attached to the edges. So between Reno and Salt Lake City, we've assigned a number, 11.5, and that can mean the traveling time, or it could mean something completely different. We assign the meaning to that number. One of the famous problems associated with weighted graphs is the traveling salesman problem. So this is where a traveling salesman wants to visit cities in a certain area, and there's some weight associated with the cities that they want to visit. So maybe it's distance, maybe it's travel time, something like that. And they want to select the route with the least total length. So they don't want to use all that much gas. They want to optimize for the least total length. And so the question here is, what path should they choose? And then in doing so, we find out what's the length of the least total length route. So there's a problem in the packet, which seems a little bit tedious, but I think the point is to do trial and error, to just see what works. Like, does this path work, or does this path not work? So take a few minutes, maybe talk with your neighbor and see what path you can come up with. So this is the zookeeper, problem 11. Once you find the route, let me know. All right, did anybody find the route? Yeah, what's the route that you found? Yeah, yeah. So that's what the book says too. How did you figure that out? What was your process?
Do others first, and then I realized that out with that at 10 or the 11.
Mm-hmm.
Just picked all the other lowest ones to that, and then
Yeah. Yeah. Anybody else approach it? What kind of things were you trying? Even if they were wrong. Okay. Yeah. So the traveling salesman problem is a difficult problem, right? With 5 points here, it's not too bad. Like we can use trial and error to figure things out. The traveling salesman problem is actually like famously known as like a really hard problem. And that's just how it is. So once we add more cities or add more um, animal enclosures in our zoo, then the problem gets to be more tedious and what computer scientists call really, really hard. Uh, so yeah, so that's the thing about graphs. Some problems are fairly straightforward. Other problems are a lot harder depending on what we're trying to do. Another kind of graph that you'll be learning about is a digraph, which is also called a directed graph. I mostly call it a directed graph, but digraph is also accepted. That's mostly just personal preference, not correctness in any way. And that's just, I call it directed graph because it's more clear to me, here's what's going on, which is where we've got a regular graph with vertices and edges, but we add arrows to the edges now to say that, for example, this is like a street diagram where each intersection is a vertex. So each intersection, like A is an intersection, D is an intersection, E is an intersection, and they're all one-way streets between these intersections. And we draw a line, we draw an edge between two intersections if that street is one way. And so we draw the line with an arrow in which way the direction is going. So like the street goes from D to A, from D to E. So yeah, so we draw that line with the arrow. And so then there's a packet problem here, which is to represent it by a directed graph. So if you want to work on that, and then I'll give you like 2 minutes to do that, and then I'll have someone come up and draw it on the board. All right, if someone's done, do you want to come up and maybe move this up? And then if someone wants to grab a marker. Otherwise, I will pick someone. Well, you're up. Do you have a solution? Yeah.
Just drawing the map, but right, and then just putting the points where
Yeah, so
they
the,
intersect.
yeah. Cool, thank you. All right, so A is St. James and Piccadilly. B is Piccadilly and Regent. C is Piccadilly and Haymarket. D is Haymarket and German. E is German and Regents, Regent. E is St. James and German. No, F. G is Haymarket and Hall Mall. H is Pall Mall and Regent, and I is Pall Mall and St. James. Does that line up with what everybody else got? Yeah. Awesome. Okay. Thank you for that. So then there's the word network, which the textbook says that digraphs plus edge weights equal a network. In truth, any graph, you can call pretty much any graph a network. It doesn't have to be weighted, doesn't have to be directed. But sometimes it's helpful to say that this kind of graph is a network. But the idea is that we can use graphs and say that we've got a network to represent any kind of network that we apply that term to in real life. So like the highway system, that's a road network. You can have a rail network like BART or Muni or Amtrak. Television networks or electrical networks that have like power lines that go somewhere. Also for phones and also like social networks. So when we combine this, then there's an opportunity that it lets us model some pretty complex problems, and then we can figure out how to solve them fairly easily. In terms of edge weight, we kind of talked about this already, where edge weights can mean whatever we want them to, right? Like it could be the length in miles. It could be, here's how long it's going to take to drive, assuming you're going at some speed. It could be like if I'm going up to Napa, for example, there's an $8 toll that way. But if I found some other way that didn't have a toll, then that cost would be 0. It can also be something completely subjective, where we can say there's some beauty score that we assign to the scenery as we drive this road. It could be, oh, maybe this road is dangerous. Maybe there's a lot of potholes. Maybe we count the number of potholes and we assign that number to the edge. Any other things you might think that we can add? Like, what could we assign? What could we say edges mean? Or the number assigned to edges? Any ideas? Yeah. Yeah. So maybe you're listening to like the Taylor Swift album, and how many of those songs can you get through from here to Chipotle? Any other ideas? Yeah, so it can be like completely arbitrary. We're the designers here. We decide what these numbers mean. One of the common problems that you'll see is shortest path, which is if you've got two vertices, you want, and if there's, so shortest path is the problem with weighted and unweighted graphs. So the problem 13 is weighted graphs. If for an unweighted graph, it would be with the least number of edges. But with weighted graphs, you assign the shortest element to what's the least amount of numbers that you can add up. Yeah, so I'll you do problem 13, which is finding the shortest route from S to T. So which is kind of like traveling salesman, but a little bit different. All right, anybody find the path? Go for it.
think it's S to A and A to B and C. I mean, E to C and then C to D.
Right, yeah. Why'd they give you the hint of A to T and B to T? What was the point of that? If you used that hint, did it give you any useful information? What kind of information?
So that is kind of
Yeah, because going from S, we have two options, right? There, from S, you go to either A or B. And so if you find the path from A that's shortest, then the path from B that's shortest, then you know that from S, you just choose the one that you found for A. Awesome. Thank you. A kind of variation on this problem is what we call a flow network or pipeline network. The idea is that we're modeling kind of some fluid network like the water system or another kind of pipeline, right? Could be like electricity, where the wires that are connecting to vertices can only handle like a certain amount of current. Or if we're in the water network, each pipe has a capacity and we can't exceed that capacity or else everything's going to break. So the point is that fluid is going from one point to another. And the general question that we want to answer with these kinds of problems is what's the maximum flow? Where we want to find the path that takes us from one point to another, but with the largest number that we can look at. So let's pull up this, and you can't see that, so let me share this. You also still can't see that. Okay. Right. So the idea is when you've got a flow network, so it's directed now, right? There's arrows to the edges. And so if each of these is one pipe or one wire that is only rated for a certain amount of current, we want to find what's the most amount of current that we can flow in this network from S to T. And one of the changes from the previous problem is if we really, really wanted to, we could go like we could go S to A to D, back to B, up to C if we wanted. Like you can go backwards because there's no direction on these edges. But here we are constrained. And so the trick here is maybe if I think S to C is best to start off with, because it's 14. The idea is if you follow that through and try and see, maybe the number is lower. So I'll give you a few minutes for this one too. Try and figure out first of all, what's the path? And second of all, what's the maximum amount of flow? Did anyone find it? Yeah,
I got 53.
53.
From S to C, then from C to E, then E to H.
Hmm. Okay, so I think I must not have explained it correctly. That's my bad. Sorry. So for this problem, we're not looking to add everything up. In this problem, we're looking, um, so let's say from S to C, that's capacity of 14, right? If you imagine water going through these like a pipeline network, so 14 units of water. But then from C to E, it only is rated for 12 units. And so we can't send 14 units in total from S to E, right? Because that's going to break the segment from C to E. And so, and then if we were go from H to T and take that, like the underground path, we can't send 14 units of water through this path because it's going to break everything after S to C. And so it ends up that the maximum flow is the smallest number on your path because we can only send 6 units total if we choose this bottom path. Does that make sense? Yeah, and so the question is like, so if the maximum flow is the smallest number on our path, what's the biggest possible number that we can find? So the answer the textbook gives is actually S to A to D to G to T. And trying to think about it, like if we took the bottom path, that would give us 6, and 7 is bigger than 6, so we would, let me actually look up my tablet. Yeah, so make it red. So this path capacity is 6. If we take the top, the capacity is 7. We could try, like, if we went to B, we would have 6, which already is less than 7. So if we found the top path first, then we would know that, like, we can't go to B because that's automatically less. But if we did go to B and then we chose to go to either D or E, then you would see that we've got 4 as an option, which is less than anything else that we've seen so far. So that disqualifies it. Yeah. I think max flow problems are really interesting. If you end up taking like higher level computer science classes, like in grad school or something, chances are you're going to look at something called min-cut max flow theorems, which combine the network flow aspect with other kind of topics in graph theory, which is hard, but it's really interesting. And I think it's also like useful problems, especially when you choose to go and model something that has a capacity like this. Okay, let's go back to the slides. All right. Thank you for that. Now we're on our last page of the packet, so chances are we are gonna finish chapter 1 today. Hooray! And so this is the kind of question that I hope the homework will help answer for you of why are we looking at graphs? Why bother? Because graphs are just representations of some model. So you can say like a graph can model a highway network. A graph can model an electrical system. A graph can model a network of friends. So that's kind of also why I did the abstraction exercise, which is where like if we're talking about a group of friends that we want to model, maybe there's like low-level details of person A is friends with person B, but not when they're in 2 different classes or something like that. Like there's some low-level details that we as humans look at when we're looking at our friend group. But in terms of a graph, we kind of want to rise above that and just say like A is friends with B, B is friends with C, and just looking at the high-level details. When you're looking and trying to do homework 1, graphs are typically representing structural features. And so that's where abstraction comes in to try and figure out what are the important structural things that I want to model here. So problem 15 is just fill in the blanks. So got model and then elements of the structure tend to be vertices, and then the connections or the relationship between the things are the edges. Anybody need more time? Okay. So then we're going to briefly talk about what kind of problems are we going to look at. So there's 4 main types of graph problems, and this is also one of the packet problems, I believe. We will also see this at the end. So I'm going to go through each of these. I've got like a slide for each of them. So don't worry about writing it all down right now. Where we've got existence problems, which is looking at, does there exist something, or is it possible to do this? That's an existence problem. We'll look at construction problems, which is assuming that it exists, how do we make it? That's an important kind of graph problem. Enumeration problems, which is how many are there? Can we list them all? Then optimization is which one's the best? Okay, so for existence problems, an example of that is it possible that there's a solution to the Königsberg Bridge problem? If there is, then we have to show a solution, and that's a way to answer our question of does there exist a solution here? But if there's no solution, then not having one isn't proof. We have to actually prove and show that this the answer to this question is impossible. For construction problems, we ask if a solution exists, how do we build it? And so some of the easy examples we can come up with trial and error. For harder examples, we'll need something like an algorithm to show here's how you would construct this structure in a systematic way. Does everybody know kind of like the definition of an algorithm? You should probably know this because 222 is a prerequisite. But like an algorithm is the step-by-step process to get to the end result. For enumeration problems, we're looking at the question of how many solutions are there? What do they look like? There's an option we could also like count how many graphs of this type exist. And we can also list them of here's what each type of graph is. And then there's optimization, which is getting into, again, what is best. So if we define best as like fewest transfers on Muni, how do we get from point A to point B? And that's an optimization problem of we're going to give some sort of algorithm to say, here's how to choose the best route every time. Okay, here's that slide again. Does anybody need more time writing it down? Okay, I'll hang on for a second. Oh, the other problem for this one, the last one on the packet, 17, which is once you've written down, here's the 4 kinds of problems, ask. There's some sample problems that I've chosen from the textbook from later chapters. And so it's just practice in looking at these problems and trying to classify what are from these categories, what kind is the problem? Anybody have any ideas? How about, let's look at, are there any simple graphs with degree sequence 1, 2, 3, 4? What kind of problem do we think this is? Yeah. Existent, yeah. Like, are there any graphs with this property? Yeah. What about the draw the 11 unlabeled simple graphs with 4 vertices? Construction, yeah. Yeah. I think maybe like this one maybe could go multiple directions, but yeah, construction. The next one is also probably very obvious, given that it starts with construct. What about the Knight's Tour?
Existence.
Existence. Is there? Does there exist? What was the thing I was thinking of? I think, oh, sorry. I think the 11 unlabeled symbol graphs could also count as like enumeration, because part of enumeration is like, can we list them all? And so the problem here is list them all. Anyway, it included like one of each of them. How about the last one? Coloring edges greedily.
It's optimization.
Yeah. Because like greedy algorithms is something that we'll probably get into. Yeah, that's a way to do something. And so to color the edges of a graph greedily, the optimization is geared towards doing this a certain way. Okay. Just some final slides over here. Some questions that we can ask as we approach graphs. So like if you draw a graph for your homework, then we can ask, like, can we show that a solution exists? Can we show there's no solution at all? Is there only one solution? Or if there are more, can we define what's best? Other things you may want to consider is, do we need to find something exactly, or can we approximate? If we have an idea for a graph, are we going to construct it actually, or can we just describe, here's what it looks like? That's a typo. Can we develop a method that gives the correct answer in every instance? So these are all questions that we are going to have practice with as we go through the class. And like I mentioned before, some problems that we're going to look at are harder than others. So something like the shortest route, we can say is quote unquote easy, but something like the traveling salesman problem is quote unquote hard. If so, we probably, I don't want to promise anything or not promise anything. But depending on how far we get, there's something called P versus NP, which basically says this is a hard problem, or we can solve this problem in linear time. That's P versus NP. So if you're interested in like what's a hard problem, I encourage you to look it up. We may or may not get there near the end of the class. Okay, so that's the end of chapter 1. Congratulations. For where we go from here, let's see, we've got like 15 minutes. So I figure we'll start the math background. But I will have you turn in your packets now, and I will pass out the other ones. And for those of you who are also in 374, I will have you, so we're about to do the same unit twice if you're in both classes. That's just because the math background in both of those classes is really important. And I want you to have a firm understanding of these topics. I'll show you the Canvas page. So the Canvas page, so if you're in both classes, this unit is going to be exactly the same. So I'll just have, if you're in both classes, just write like I'm in 485 and 374, and just turn in one copy and you don't have to do both. I need to fix that. 30 points, and you can submit it online if you so choose. Yeah, so the idea with this packet is we'll talk about things in class. We may not get to all the problems in class. But you can start it and then go through it afterwards and make sure that you touch every question. And then when you turn it in, I'll give 10 points for completion, which is just the normal packet thing that I'm going to do with this one. And then 20 points to make sure that everything is correct. So if you're in 374 as well, just turn in one copy. Okay, let me pull this up. Okay. So we have to talk about mathematical background, even if some of you have taken discrete math, because some of you have not taken discrete math. And so the goal here is just to level the playing field and make sure that we all have the tools and the language to approach the problems that we're going to do in this class. The idea is that this won't take us very long, and it should be fairly easy if you've taken discrete math. And hopefully it's an easy on-ramp if you haven't. So the things that we're gonna go over are, we're gonna go over set theory basics. We're gonna talk about Boolean things, like what's a Boolean statement, what's Boolean operators. We'll go over some, what I call baby proofs, easy proofs. Talk about the different proof styles, and then for the rest of the homework on the packet is just more practice on that. Okay, so we're going to talk about a few things for a set. We'll get through all this list. So a set is a collection of things. That's the basic definition, where we've collected some things and they live in our set. So like over here, we've got a set of polygons, which we represent the set as just a circle. And there's all of these different polygons. There's a square, a triangle, another triangle, trapezoid, and so on. Anything that we want can be in a set. We can have a set of fruit or a set of numbers. The order in a set does not matter. So this set of cherry, banana, apple, and is that a kiwi? Yeah, so this set of fruit could be completely swapped up. It could be the kiwis first, and then the banana, and then the cherry, and then the apple. It's still the same set. So order does not matter. The only thing we can say about the set is that repeats aren't allowed. So if we write a set with repeats, it's the same exact thing as a set written without repeats. And the way that we write a set is with the curly brackets, and the things that are in the set are in the middle, typically separated by commas. So the picture of the fruit here, we've got the curly brackets. If we add commas between the fruits, then we're good to go. Okay, so the first question on the packet is just fill in the blanks, true or false. Or does order matter in a set, yes or no? In terms of elements, we say that a member of a set, so for example, the banana is a member of the set apple, or apple. The banana is a member of this set in general. We say that the banana is an element. So a cherry is also an element of that set. So for example, in this set of students, you are an element. You're a member of this class. If you were all sitting in completely different places, you're still a member of this class. We write the element of operation with this, this little E type thing. Let me draw on here. So it's kind of like an epsilon. If you care about writing LaTeX, it's \n. And the way that we read this sentence in math is X is an element of the set A. That's how we read that. Okay. We can represent nothing at all also with set notation, where we say that the set of nothing is called the empty set. The empty set contains nothing. There's nothing in the empty set because it's empty. The way that we write it, we either write it with curly brackets that don't have anything inside them, or rewrite that as like a 0 with a slash through it, that's exclusive. So either you choose one or the other. It's not curly brackets, empty set inside and curly brackets. That's something different. That says it's the set containing the empty set, which may break your brain a little bit, but it actually means something different. So this is the empty set. This has nothing in it. So the size is 0. This is the set containing the empty set. It has something in it, even if that something is nothing. So the size for this set is 1. So just remember it's either one of these or the other. For subsets, we can say like so the example in the packet is like let's say 1, 2, 3, 4. We can say that 2 and 3 is a subset of that. So it's some elements that are also in the bigger set. So it's like if we picked something out of our bag of fruits, those fruits are a subset of the bigger set. So yeah, so subsets of A, B, C, D include maybe just A and B, and just B and D. Another subset of every set implicitly is the empty set. So it's like if we reach into our bag and we pull out nothing. That's still technically a subset. Yeah, so we should include the empty set, and another subset, like a trivial subset, is the set itself. So ABCD, a trivial subset is ABCD. If we want to list all of the possible subsets, which one of the packet problems require you to do, that's called the power set. So the list of all possible subsets. So can anybody tell me what's all possible subsets of the set apple, orange, banana? Or tell me some of them, and then we can figure out the rest of them. Yeah.
Null set, instead of just apple, just orange, just banana, and then apple orange, apple banana, orange banana, and then apple orange.
Yeah, simple as that. Just all the different combinations of the things in the set. How many subsets are there in that list? Empty, the single elements, the double elements, and then the full set. So there's 8 total. So something to think about, if you've taken discrete math, you probably already know this. But I would encourage you to think about what is look at apple, orange, banana, and mango, and try and figure out how many possible subsets there are there, and then try and come up with an equation in terms of the size of the set. So if we say so here the size of the set is 3 and 4. If we say the size of the set is n, can we write an equation in terms of n to express how many possible subsets are there? Again, if you've taken discrete math, you probably know this. But if you don't, something to think about. And also for homework. All right, so we'll move on. In terms of how we add to a set or subtract to a set, what do you think adding to a set means? We've got our set of fruit. What does it mean to add something to a set, to the set? Any ideas?
that set, so like orange is in there, adding an orange would be like cherry, banana, apple, kiwi, orange.
Yeah, exactly. Yeah, so like adding another element there. And subtracting a set we may think something similar, like maybe we take out apple. So there are mathematical concepts that do something like this. So one of them is the union, where we combine two sets. So the example for adding an orange would maybe, if we said like was it cherry, banana, apple, and kiwi, and then we want to add orange, we would have a set containing orange, and then we just union the two. And what union does is it smushes them together. So everything in set A and everything in set B. So we can say original set is A and the set containing orange is B. There's no restriction on there needing to be anything in either A or B. So just having one thing in B is fine. If B was just the empty set, that would also be fine. If B had 5 million fruits in it, that would also be fine. So there's no restriction on that. The result of the union operation is just everything in A plus everything in B. And if there's any overlap, anything in both, then we don't write sets with repeats, so it's just no repeats. This is equivalent to the logical OR operator. We'll talk about that in a minute too. In terms of subtracting, so let's say if we had like a cherry, a banana, maybe an apple, and kiwi over here. Cannot tell that because it's red text. Can I change the color? Cherry, banana, kiwi, and apple. Slightly better. So the way that we would take apple out is we would have A, B, our original set of fruits, and then B is the one that we want to take out, so the apple, and we write with the backslash, and that means set difference. So we're taking away, so we have, the result is going to be everything in A, but minus the thing that's in B, the things that are in B. And so we can represent these with Venn diagrams where we say like, if this is the one on the left is A, the one on the right is B. Okay, so I think we're pretty much out of time. We'll pause here and continue on Thursday. We'll finish this on Thursday. So we'll be good to go. I don't think I have any announcements for you. Work on the homework. That's my announcement. Thank you, and I'll see you next time.